Alright, so imagine you're looking at a curve, right? Say like a roller coaster. Yeah, say you're looking. Alright, so say you're looking at this roller coaster, and somebody comes up to you and is like, "Yo, bro, what if that roller coaster was actually represented as a vector valued function in 3 space, and we could make entire new rectangular coordinate systems for each point on the roller coaster, and maybe even describe how the roller coaster's track is continuously curving through space." And you're like, "Dude, what the hell are you talking about?" Well, in this video, we're going to answer that very question and a lot more questions related to that. Alright, so say we have this function r of t right here. R of t's graph generates a curve C. And so we want to find the vector tangent to the curve C at any t value such that the norm of the tangent vector is 1. Well, we already know that the derivative of r with respect to t is tangent to c. So now we just have to normalize the derivative of r. We'll do that by dividing the derivative of r by the norm of its derivative, and that gets us this right here. So now we have a definition for the unit tangent. And so a natural question after doing that is, what happens if we differentiate the unit tangent? Well, it turns out that since the norm of t is 1, t prime is going to be orthogonal to t. And to see why this works, let's imagine a circle with its center at the origin in the xy plane. And let's make a vector from the origin to somewhere on the circle. This vector's derivative will always be orthogonal to itself, no matter where it is on the circle. So now we'll make v here a function of t. V of t's norm is always a constant c. And so is t's norm. In this case it's 1. So we come to the conclusion that if norm r of t is a constant, then its derivative is orthogonal to itself. Even if r's graph is only a small part of a circle, its norm is still a constant. And this makes it so that its derivative is perpendicular, as we can see from this circle example. So now we know that t prime of t is perpendicular to r of t's graph. Since t prime is perpendicular to the graph's unit tangent, which is just t, and this allows us to make a new vector, which is called the unit normal, and is just a normalized version of the unit tangent's derivative. Alright, so before we go on to the next part, I want to show a nice result about unit normals that I found recently. And it's the fact that unit normals always point towards the concave side of any vector function's graph. And what I mean by this is, say we have this curve C, which is just the graph of a vector function, and we get the unit normals at all these points. You'll notice that all the unit normals point towards the concave side of a distinct part of C. And the proof for this is kind of cool, so I want to show you guys. We start off with 4 definitions, obviously unit tangent and normal. Over here we define n of t as the unit tangent rotated pi on 2 radians counterclockwise, and then phi of t, which is the angle between I hat and the unit tangent. One of the main properties of vectors is that if phi is the angle between I hat and v, v can be expressed as x component, which is norm v cos phi, and its y component, which can be expressed as norm v sine phi. We'll do this with the unit tangent too. We don't see the norm here because it's just 1, it's a unit. And we'll express n of t the same way. What? The same way? By adding pi on 2 radians to phi of t, since n is just t rotated pi on 2 counterclockwise. Now we're just going to simplify the components of n into this using angle sum identities. So we now get our n of t as a vector function. We now need to observe that for intervals where phi increases as t increases, n faces the concave side of C. But for intervals where phi decreases as t increases, n faces the convex side of C. We're now going to differentiate the unit tangent with respect to t using the chain rule. We're using the chain rule because the unit tangent is a function of a function, which is phi, which gets us this. But this vector is actually just n, so we'll just rewrite this as n of t times phi prime of t. Phi prime is positive for intervals where phi is increasing as t increases, but it's negative for intervals such as these where phi decreases as t increases. What this is saying is that for intervals where n faces the concave side of C, t prime is facing the exact same way. But for intervals where n is facing the convex side of C, t prime is facing the exact opposite way. Or in short, t prime always faces the concave side of C. And since the unit normal, which is n of t, is just a scalar multiple of t prime of t, this means that the unit normal always faces the concave side of a vector function's graph. Oh yeah. Alright, let's get back to the main idea. I have to preface that this result is only true in 2 space, not in 3 space. So now we have the unit tangent and the unit normal, which is perpendicular to the unit tangent. So what now? Well, this is where we introduce b of t, which is also called the unit binormal, which is just the cross product of the unit tangent and normal. Wait, a unit vector equaling the cross product of 2 other unit vectors? That reminds me of something. BANG! Yeah. We've now made a vector b mutually orthogonal to t and n the same way that k is to I hat and j hat. The plane that t and n makes is called the osculating plane. The plane that t and b makes is called the rectifying plane, and the plane that b and n makes is called the normal plane. If you take the unit tangent, normal, and binormal of a vector function, they kind of describe an ever-changing rectangular coordinate system that changes based on where its origin is on the graph of the vector function. This whole thing is actually called a TNB frame. This is an example of one right here. Look how beautiful that is. They can actually tell you a lot about how a particle moves through 3D space. Physicists use this stuff all the time in their works. Also, notice this red one right here? That's the unit normal. Obviously, it's normal to the tangent, but also, it's pointing inward all the time because it's pointing towards the concave side all the time. I proved that earlier! But, anyway, you can go tell that guy that bothered you while you were looking at that roller coaster to freaking go away, because he's a weirdo. Alright, bye.